Hello dear students, welcome again you all of you in this statistical mechanics lecture. So far we are discussing about the unit number 3, that is the quantum statistics techniques, and we have discussed about the density matrix, and we have derived the expression for density matrix for this canonical ensemble and grand canonical ensemble. So in this today's lecture we will derive the expression of a electron in a magnetic field, and we will find out the expectation values of the Pauli spin operator. So let us start our today's lecture. So the first example is an electron in an magnetic field. Now a single electron which is moving in a microcanonical ensemble. So this single electron possess, so first it has an intrinsic spin of S cap, which we generally represent as 1 by 2 h bar into sigma cap, where sigma is the Pauli spin operator, and the value of this spin, because it is moving along this three dimension, so value of this intrinsic spin Sx, so that is 1 by 2 h bar sigma of x, Sy, that is 1 by 2 h bar sigma of y, and along Sz, that is 1 by 2 h bar into sigma z, where sigma x, sigma y, and sigma z, they are known as the Pauli spin matrices. And the second, that is the magnetic moment of this electron, so which is generally represented as mu b, which is E into h bar over 2 into mc. So where m is the mass of this electron in SI units. Now spin of the electron, it can have two orientation. Either it can have a spin up spin, that is along upside, or it can have a down spin, so with respect to an applied magnetic field. Now if B is the magnetic field which is applied along this z axis, then this total energy, so h bar, so that is equal to minus mu dot B. So here beta, that is the applied magnetic field. So mu, so we know that is it is equal to E over mc into this spin matrix. So putting the value of this spin matrix, m into c into h by 2 into sigma. So this EH over 2mc, that is the mu b, that is the magnetic moment, into sigma. So putting these values, so this Hamiltonian operator h cap, this becomes minus of mu beta into b into sigma cap. So let us say this is our equation number 1. Now in this canonical ensemble, the density operator, so in the canonical ensemble, so the expression of this density operator, it is generally defined as exponential of minus b into h cap over this trace value, that is the sum of all these values, which is generally known as the partition function. So Now we will solve this equation separately. So first we will solve this numerator, and then we will solve the trace value, that is for the denominator term. So exponential of, so solving equation 2 separately. So exponential of minus beta into h cap, so this becomes exponential of beta into, putting the value of this h Hamiltonian operator. So this is beta, this is b, that is the magnetic field, into sigma z. So putting the value of this Pauli spin operator, which is along this uh, z-axis. So here I would like to explain the representation of these Pauli spin matrices. The sigma x, that is equal to 0 1 1 0, that is 2 cross 2 matrix. Sigma y, that is 0 minus of iota into 0, and sigma z, that is 1 0 0 into minus 1. Since we are applying this magnetic field along this z-axis, so we will consider this Pauli spin matrix along this z-axis. So putting the value of this sigma z operator in this equation, so this equation becomes exponential of beta mu b into b into 0 0 exponential of minus beta mu b into beta. So this is our numerator term for this equation 2, and taking the sum of these matrices. So when we solve this equation, so that is solving this matrix, so this becomes exponential of beta mu b into b plus exponential of minus beta mu b into b over 2. So this is equal to 2 into cos hyperbolic beta mu b into b. So putting the value of this numerator and denominator term in this equation 2, so the expectation, our density operator, so this comes out to be equal to 1 over exponential of beta mu b into b plus exponential of minus beta mu b into b into exponential of beta mu b b 0 0 exponential of minus beta mu b into b. So solving this, so the expectation value of this sigma z, so this comes out to be trace of density matrix into sigma z matrix. So this becomes trace of exponential of beta mu b into b into 0 0 exponential of minus beta mu b into b, and sigma z is 1 0 0 minus 1 over this trace of sigma density into h. So that is equal to 2 cos hyperbolic beta mu b into b. So this Pauli spin matrices eigenvalue, that is sigma z, this comes out to be trace of exponential of beta mu b. So when you multiply these two matrices, so this comes out to be 0 0 exponential of minus beta mu b into b over 2 cos hyperbolic beta mu b into beta. So solving for this sigma z, so that comes out to be exponential of beta mu b into beta minus of exponential of minus beta mu b into beta over 2 cos hyperbolic beta mu b into b. So this is sine hyperbolic. If I multiply by 2 and divide by 2, so this becomes 2 sine hyperbolic beta mu b into b over 2 cos hyperbolic beta mu b into beta. So sine over cos, that is equal to tan hyperbolic of beta mu b into b. So this is the expression of the expectation value of Pauli spin operator if the electron which is moving along the z-axis in magnetic field, so that is the expectation value of Pauli spin matrices. So the next example that is related with is the free particle which is moving in a cubicle box. So that is along the three-dimensional cubicle box of side L. So example second is, which is related with this canonical ensemble, is the free particle in a cubicle box of side L. So when this particle which is moving along within this cubicle box, so the total energy, the total Hamiltonian, so this particle which is moving having a momentum of p, so p square operator over 2m, so the Hamiltonian function that is equal to the total kinetic energy of this particle, so which is moving with the momentum p. So putting the value of this p operator, so this comes out to be minus h square del square over 2m. So opening this equation for this del square, so del square is, since the particle it is moving along the three dimension, that is curly square over curly x square, curly square over curly y square, plus curly square over curly z square. So the eigenfunctions of this Hamiltonian operator H, they satisfy the periodic boundary conditions, and the particle which is moving with the wave function, so this can be written as x plus L. So if it is moving along the x-axis, and it is equal to x y plus L if it is moving along y-axis, and it is equal to x y and z plus L if the particle it is moving along this z-axis. So this is equal to x, y or z. So if it is moving along this three dimensions which is having a wave function of phi. So this wave function phi, so it can be written down in terms of energy, that is equal to 1 over L raised to power 3 by 2 into exponential of I k dot r. So putting the value of this energy eigenvalue E, so E basically it is equal to h square over k square into 2m, and our Schrodinger wave equation, so Schrodinger wave equation becomes del square psi x over del x square plus kx square into psi x is equal to 0. So where kx, that is the wave vector for this wave function psi. So if the particle it is moving along this x-axis. So the solution for this Schrodinger wave equation, the possible solution of this wave function psi x, so it comes out to be a sine of kx into x. I will not derive the solution because you all are familiar with this solution of a free particle within a box, and you have studied during your graduation classes in the quantum subject. And since a is the amplitude of this particle, which is equal to 1 over under root of L sine of kx into x, and the maximum value of kx, which is of the order of 2 pi nx over L. So from this, the value of Hamiltonian, it comes out to be minus h square over 2m into del square. So this can be written as h operator into E. So that is E into E operator. So h operator into psi E, which is the function E into phi E. So the value of this phi E, so it comes out to be 1 over, since this is for x-axis, and the same value it will equal to for y-axis, and the same value it will be equal for z-axis. So when we add up all these values, so it comes out to be 1 over L raised to power 3 by 2 exponential of I k dot r, and this expression we will derive in our next slide. Now how we can evaluate the canonical density matrix for this free particle which is moving in this cubicle box, and the expression of this density matrix, which is exponential of minus beta into h cap over trace of exponential of minus beta into h cap. Any operator, so a, so it can be written as a operator multiply by this identity matrix, so which is in terms of this energy. So our numerator term, so it comes out to be exponential of minus beta into h cap, so that becomes minus beta into h cap into summation of identity operator. So we can keep these exponential term within this operator. So this we can write down as exponential of minus beta h cap into E operator. So in this coordinate representation of this density matrix, so similarly, so we can write down this density matrix representation. So that is equal to x density matrix along x-axis, density matrix along y-axis, and density matrix along z-axis. So this becomes exponential of minus beta into h cap into r dash, so that is a summation of r dash e exponential of beta e into e over r dash. So this comes out to be summation of exponential of minus beta e and 1 over L cube exponential of I k r minus r dash. So putting the value of this phi e and its complex conjugate, so phi e of r, so that is equal to 1 over L raised to power 3 by 2 exponential of I k dot r, and its complex conjugate, So phi e star, that can be written as 1 over L raised to power 3 by 2 exponential of minus I k dot r. So phi e and phi e star, so this comes out to be 1 over L cube exponential of I k r minus r dash. Now solving these equations separately, first for x-axis, and then we will improvise these equations similarly for y-axis and for z-axis, and then we can derive this expression along this 3-axis. So this equation of r exponential of minus beta h operator into r dash, so this comes out to be 1 over L cube summation of exponential of minus beta h square k square over 2m into exponential of I k r minus r dash. So this equation becomes 1 over L cube summation of, so this is along all these axes kx, ky, kz, which varies from minus of infinity to plus infinity, exponential of minus beta h square over 2m, and this k square, it can be written as kx square plus ky square plus kz square, and exponential of I kx into x minus x dash plus I ky y minus y dash plus I kz z minus z dash. So for if the particle it is moving only along the x-axis, so then we can write down this equation as exponential of minus beta into h operator along x-axis into x dash. So this comes out to be 1 over L summation of kx, which varies from minus infinity to plus infinity, into exponential of minus beta h square over 2m into kx square into exponential of I kx into x minus of x dash. So solving this expression, so this comes out to be 1 over L summation of kx, which varies from minus infinity to plus infinity, exponential of minus beta h square over 2m. So putting the value of kx, that is equal to nx square into 4 pi square over L square plus this exponential value, it comes out to be kx, which is equal to 2 pi nx over L into x minus of x dash. So solving for this limit which varies from minus infinity to plus infinity, so this expression, this summation, we can write down into in terms of integration. So this we can write down as integration of minus infinity to plus infinity 1 over L into dn of x, and if we keep all these bracket term as it is, so this we can write down as 1 over L into L over 2 pi into d into kx. So this comes out to be integration of minus infinity to plus infinity 1 over 2 pi into d into kx. So putting these values in this above expression, so this equation becomes xo exponential of minus beta hx operator x dash. So this comes out to be 1 over 2 pi integration from minus infinity to plus infinity into d into kx, and all the bracketed term, that is the exponential term beta h square over 2m into kx square plus I kx into x minus of x dash. And using the standard result of integration, so we know the integration of minus infinity to plus infinity of exponential of minus 1 by 2 ax square plus ixy, that is into dx, is equal to under root of 2 pi over a into exponential of minus y square over 2a. So here in this we have the same integration, and we have a value of a which is equal to beta h square over m, and value of y which is equal to x minus x dash. So putting the values in the same integration, our expression becomes to x dash, so that is 1 over 2 pi under root of 2 pi over a, where a is beta h square over m into exponential of minus x dash square over 2 beta h square over m. So when we solve this, this comes out to be m over 2 pi beta h square into exponential of minus m into x minus x dash square over 2 beta h square. So this is the result for the value of this total energy. So that is exponential of minus beta into hs operator. So when the particle it is moving along this x-axis, so similar result it could be obtained for y-axis and along z-axis. So our expression, if the particle which is moving along these three dimensions, so from a region r to r dash, so this expression comes out to be x exponential of minus beta hx x dash, y exponential of minus beta y dash to z exponential of minus beta hz into z dash. So this expression is similar for x, y and z axis. So multiplying the same expression 3 times, so this comes out to be m over 2 pi beta into h square raised to power 3 by 2 exponential of minus m over 2 beta h square x minus x dash square plus y minus y dash square plus z minus z dash square. So this comes out to be minus m over 2 pi beta into h square raised to power 3 by 2 exponential of minus m over 2 beta h square into r minus r dash square. So once we find out the value of this exponential of minus beta H operator. So from that we can find out the trace value if we take the total integration of this expression. So the trace of exponential of minus beta into H operator. So this we can done exponential of minus beta H operator R dash d cube into R. So this comes out to be exponential of minus beta h, that is equal to m over 2 pi beta h square raised to power 3 by 2 integration of d cube R. So which is equal to the total volume of this confined region, that is the characterized volume. So this expression comes out to be 2 pi beta h square raised to power 3 by 2 into V. So that is generally known as the partition function of a single particle. So that is the trace value. So this we have already derived in unit number 2 while solving the partition function of a canonical ensemble. So this expression is known as the partition function of a single particle confined to a box of volume V. So putting the value of this exponential of minus beta, this value and trace value, we can find out the density matrix operator for this free particle in a box, and this expression comes out to be R dash, that is exponential of minus b h over trace of exponential of minus b h operator. So this is equal to 1 over v exponential of minus m over 2 beta h square into r minus r dash square. Now this equation, it has its physical significance, and you can see that the diagonal element which represent this density operator r to r dash, so it represents the probability density of a particle to be in the neighborhood of particle, so that is r dash. So this implies that in case of a single particle, that is the free particle, all position of the particle within the box, they are equally likely to obtain. So this is the expression of the free particle, density matrix of a free particle in a box of cubicle length L. So this is all about for today's lecture. So in our next lecture we will discuss about the harmonic oscillator problem and find out the density matrix for this harmonic oscillator, and we will discuss about the significance of this Boltzmann formula, that is for this classical and quantum mechanics. So till then, goodbye, see you in the next lecture. And if you have any doubts, you can write your queries in the comment box or ask me on my WhatsApp number. See you in the next lecture.